Okay, so we've been doing lots of work on different parts of the electromagnetic spectrum, and we've already had a little look at how light interacts with surfaces, where we've talked about absorption and reflection and transmission. We did the law of reflection, and we talked a little bit about refraction. And so we're pretty okay with how light interacts with surfaces. But one of the particular applications of this, refraction in particular, is that we are going to, that we make shaped pieces of glass like this one. So you can see that it's fatter in the middle than it is at the edges. The fact that it's circular is not as relevant. And this piece of glass, when it allows the light to pass through it, refraction occurs, but refraction occurs in a really particular way, and that results in this object being known as a lens, and it can be used for all kinds of purposes involving how we see with light. So today's lesson and the next couple of lessons are all about lenses. So I'm just going to start with a PowerPoint, which I'm going to share with you. Okay, so you can see that okay, hopefully. Okay, what we've got here are the names of different shapes of glass, but the point is that they are either fatter in the middle and thinner at the edges, which are these three here, or they're thinner in the middle and fatter at the edges, which is these three here. So which particular shape they are is largely irrelevant for our purposes. What we just need to focus on whether we've got a fat in the middle lens or a thin in the middle lens. So the ones that are fatter in the middle are often referred to as converging lenses, which is what today's lesson's about. And we'll see what that word converging refers to in a second. The ones that are thinner in the middle are called diverging lenses, and we're going to be talking about those next lesson. So today, all about the ones that are fatter in the middle, which if you've still got your camera visible on your screen, you'll see that this one in my hand it's fatter in the middle, thinner at the edges. Okay, so these are the converging lenses. So what does that mean? Why do we call them converging lenses? So here's a cross-section of the lens. And what we're going to do is shine some light at it. And so in comes the light from the left-hand side. And as the light hits the first surface, it's going to hit that at right angles in the middle here. And where it hits it at right angles, technically we're going from a less dense to a more dense medium, so it bends towards the normal, but it's already on the normal, so it can't do any bending here. And then over here, when it goes from a more to a less dense medium, technically it bends away from the normal. But given that it's already on the normal, it doesn't do any bending. What we need to look at, though, is light that is not on the normal. So what about this ray of light? In it comes. Again, no bending here because it's already on the normal. But as it gets to this point here, it's going to bend away from the normal. And that's going to bring it down in this direction. Now, if we bring another ray of light in, don't worry, Rebecca. Again, no bending at this surface because it's already on the normal. But here, it's going to go from more dense to less dense, bend away from that normal line. And look at that. Now, it turns out if we pick the shape of this curve to be just right, then any rays of light that come in parallel, and we'll talk about where they might come from in a second, but any rays of light that might come in parallel come out of the other side of the lens, and they all end up in exactly the same place. And this place that they end up in is called the focal point. So what shape is this lens actually? Well, one way that you can make this lens is actually to imagine that you have an enormous glass sphere 2-3 meters in diameter, an enormous glass sphere, and then you just get a little hammer and a chisel and just chip a little bit of the lens, a little bit of the glass off the edge of that spherical surface. So this surface here is kind of part of a very, very, very large diameter sphere. That's one way to make a lens. Okay, what's going on? So we know that we can interpret this in terms of refraction, but also, if you wanted to, you can think of this in terms of light just trying to get somewhere as quick as it possibly can. So we talked about the fact that light slows down when it's in a medium. So if the light's trying to get to this point here, what's the fastest way it can get there? Well, it's going to have to travel through the glass as little as possible, which is why it kind of takes this straight line approach across here. And then it speeds up again and tries to get through the next part. So we could think of the rays of light all coming in at the same speed, then they travel through the glass at a slower speed, but the same speed as each other. And then this ray came out first, so it has to race to get to this point in the same time because it's got further to go. This one spends a little bit longer time in the glass, but it's got less far to come out on the other side. And then this one's slightly longer again, but less time to go. It's just a way to think about it. You don't have to. If you don't want to, you can just think of it as bending away from the normal and ending up in the same place, the focal point. Okay, if we do this for lots and lots and lots and lots and lots of rays of light, then all of the rays come through and they all end up traveling through the same point. Now, if we were to place something at that point, like a piece of paper or your hand, you get a bright spot on the piece of paper. But if we don't place anything on the anything at the focal point, all the rays of light just sail straight through it and out the other side and carry on where they were going. So unless you put something at the focal point, you're not going to really know that it's there. Okay, let's leave the PowerPoint now. We'll come back to the PowerPoint next lesson. The next few slides need us to do a little bit of practical work before we can get to them. So let me leave that alone for a second. And let's ask instead, where would we get some parallel rays of light from? So imagine that we're looking at something a long way away. So I don't know, there's a tree over there and we're over here. So I've deliberately drawn that really far away and really tiny to give you the idea that the rays of light that we see are practically parallel coming from the tree. So how can we see that? So here's the sun in the sky shining down rays of light onto the tree. And we just pick one of these rays of light coming onto the tree. It hits the tree and it interacts with the tree and it gets scattered off in all different directions. So depending on exactly which bit of the tree it hits and exactly what angle it is that the ray of light bounces off at, we'll get all of this radiation coming off the tree, which is how come everyone can see the tree. Because if you're down here, you get some ray of light hit you. And if you're over here, you get some rays of light hit you. And if you're on a hand glider in the sky, because obviously you would, you can get some rays of light hit you. Everybody can see the tree. But there's your eye. It's a tiny little dot, which you might even be struggling to see on the if you're on your phone screen. And so what rays of light hit that tiny little dot in your eye? Well, it's certainly not this ray of light, is it? Now, this ray of light and this ray of light are quite clearly traveling at different angles. And that's got the effect that this one lands nowhere near you. The only rays of light leaving this tree that actually end up in your eye are the rays of light that are practically parallel to each other. I've even tried drawing these lines, as you just watched, as close together as I could, and they're still going to miss your eye. These two here. So when we talk about parallel rays of light, we mean rays of light that basically have bounced off an object or have been emitted by an object that is just so far away that only the rays of light out of all of the ones that were emitted, the ones that were traveling so close to being parallel to each other, that they all end up hitting a tiny, tiny little object like your pupil a couple of millimeters across, meters and meters and meters away. In fact, to make rays of light practically parallel for your, excuse me, for your pupil in your eye, you only need to go 10 or 20 meters, and the light is practically parallel. So that's what we're talking about. We're talking about light that has come from an object that is just about 20 meters away, something like that. So I happen to have such an object. So let me switch cameras and I'll show you the next little bits. Okay, let me show you what's going on here. So if you were in school right now, you'd have a setup like this on your desk in front of you. So I've got a whole load of equipment that we're going to be using in a second. But the one that I want to start off with is that I've got a board that I'm going to try and focus some light on using this lens. So I'm going to just put the lens in this little bit of wood that's going to hold it for us and stick it onto that. And then what you can see there is that the lens is trying to make some light appear on the screen. You can see it's a little bit brighter here. And that's because if you remember the, I'm sure you do remember what it's like in D1, over there is the window, which has got A block through it on the other side. And it's a pretty nice sunny day today, actually. And the sunlight is bouncing off the roof of A block over there. And it's coming in through my window and traveling through the lens. And the lens is doing a pretty good job of trying to pull all of that light together into a dot on the screen. So if I just move this lens to just the right place and move the camera a little bit closer, I don't know how well it'll focus if I bring it too close. Might be a bit close. Let's see how we go. Yeah, I think that's a bit close for it to focus. So bring it back a bit. Right, you're going to have to take my word for it because the camera's not showing it very well. But there is a really nice picture of A block's roof. There it is. On this screen, the kind of browny color that you can see, that's the tiles on the A block roof with the sun bouncing off it. The white area underneath, that's the sky. You can even see a tiny little bit of the tree that's between the two blocks. Now, it's not making one point because the light is coming through the window from all different places on the A block roof. So what we're getting is that a point of light from that bit of roof is landing on that bit of screen. And a bit of light from that bit of roof is all landing on that bit of screen. And a bit of light from a tip of a branch on a tree is all landing on that bit of light on the screen. So the picture that I just drew for you on the board is showing you the light coming from one little bit on the leaf. If I just flick back to the other camera. Actually, I can just move this camera. So when I drew this over here, I've drawn the light bouncing off just one bit of tree coming across and landing in your eye. But in actual fact, these rays of light from the sun, they're going to be coming down and hitting all different parts of the tree. And this picture that's going on here, that would be happening with parallel rays of light coming across from all different parts of the tree. I've just drawn one here. And so in the PowerPoint presentation, it resulted in you seeing a dot of light. But what's happening here is lots and lots and lots of sources of parallel light all over the roof of A block are making lots and lots and lots and lots of dots all over this screen. All of those dots are adding up together to make what we call an image of the object. So the A block roof is the, excuse me, is the object. And we've got an image of that object in dots of light being displayed on the screen in front of us. And the fact that every one of those dots is landing where it's supposed to be landing is what we say the image is in focus, which basically means that we've put the screen at the focal point of the lens. You will notice that there are two interesting things about the image. So if you could either write on the chat or just unmute yourself and tell me, what are the two interesting things about the image compared to the real A-block roof? Stick it on the chat or just unmute. Not like you guys to be shy. Reversed, kind of. Depends what you mean by reversed. The tree here is still on the correct side of the image. When I look out the window, the tree is on kind of the door side of the room. So inverted, that's a better word, Lucas. What does inverted mean compared to reversed? Or what do you mean by inverted? Or Joe, what did you mean by reversed? You can think of a more everyday word, although we are going to use inverted, but there's a more everyday version of it. Is it normal for the roof to be above the sky? No, well, it can mean, if you say laterally inverted, that can mean mirrored. But no, what's happening here is that the image has got the sky at the bottom and it's got the roof at the top. So in actual fact, what the lens has managed to do is flip the image upside down. And we need to come back a little bit and think about why that is next lesson. But one thing to notice is that the image is upside down. And we are going to use the word inverted for that. Also, that's the whole of the A-block roof, all fitting on that tiny little screen. So how else would you describe the image compared to the object? Smaller, yeah. Thanks, Emily. Okay, these are the two words that I want you to use. So upside down, we're going to switch to the word inverted. We've spoken before about how scientists like to use bigger words than they need to in order to make themselves sound very knowledgeable. So inverted, and also rather than smaller, we're going to use the word diminished. It's got smaller. We don't have a cool word for correct way up, so we're just going to write correct way up if it is. And we don't really, I mean, we could use larger, but we tend to use enlarged rather than larger. So those are the descriptive words that we're going to be using for the images that we are going to be making in class today. So what I need you to have in front of you is the piece of paper or an electronic version of it that I posted to Classroom this morning. So that looks like, got it around here somewhere. Looks like that. So we're going to be moving, well, I can't really move the object, but we're going to be moving the lens and the image around. And we're going to be making a note, upright, I'm using that word. We're going to use these descriptive words. We're going to say whether it's upright or inverted, whether it's enlarged, magnified, or diminished. And then we'll fill in some of these other measurements as we go. So try and have this somewhere where you can write on it, either virtually or really. And then you'll notice that there is one more descriptive word here which asks the question, is the image real? Which seems like a bit of a weird thing to say, because clearly the image is real. There it is. And this is a real image. We'll come on to what a virtual image is soon enough. Okay. In what comes next, it's going to be really helpful to know how far away from the lens the focal point is. And that's known as the focal length of the lens. So in order to do that, coughing again, all I need to do is to measure the distance between the lens and the screen. So if I just bring the ruler in here and you have a little look at that yourself. So hopefully you can see that the distance between the screen and the middle of the lens is 14 centimeters. And this is a lens that has a focal length of 14 centimeters. So on your worksheet that I've given you, there is a space for you to record the focal length of the lens. So you just need to write 14 centimeters in there. And then we're going to do a little virtual experiment. Okay. Let me get rid of some of this stuff. I'll stop sharing that. Okay, so this is the equipment that we're going to be using for this experiment. What we want to get an idea for is, what does the lens do to the light coming from the object to produce the image? What kind of images are possible from the converging lens? So over here, what I've got is just a whiteboard that we're just going to use to focus the light on. And we've got the lens. And then this time, I've got an object that is much, 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 much closer to us than the A block roof is. So I've just made a Fallabroom F, well, not a curly one. And I've got a light behind it, and I've just attached some tracing paper to a cutout in a piece of card. And all that's doing is giving me a luminous shape, a luminous object, an F that's giving out its own light. And I've picked the letter F simply because it's easy to measure and it'll be easy to tell if it's upside down or not. So the height of the image, if I just bring too many things that I need to hold in my hand at the same time. If I show you that the height of the image there is 10 centimeters, and again, there is a place on your worksheet to record the height of the object. So the height of the object is 10 centimeters. And then the light that's streaming out of that shape right now from all different places on it, so the light from here, and the light from here, and the light from here, and the light from here, it's all traveling in all different directions. And if you were standing in the room with me, you'd be able to see this F from all over the room. But we're only interested in the rays of light that are heading towards the piece of glass. So what you need to realize now that is different to before is that because the F is so much closer to the lens, and actually because the lens is so much bigger than your pupil, it is now not true. It is not true that these rays of light passing through the lens are parallel to each other. If I just spin the camera around and draw you a picture on the board, then really what we're looking at is, here's a whole load of light that's streaming out of here in all different directions, like the F from the side, and then there's the lens there. And so it's not just parallel rays that are going through this. You've got light from down here coming up here and light from down there going down there. And generally speaking, the rays of light are not parallel to each other. Even if we look at the rays coming from just a single point, so that ray of light going through there, from that single point, we've got rays of light traveling through the lens that are not parallel to each other. So we've just seen what a lens can do to parallel rays of light. Now the question is, what can it do to non-parallel rays of light? What will the light do to it then? Well, it turns out that it still does the same thing most of the time, just the distances get messed up a little bit. So I can move the screen and you see that it does produce an in-focus image of the object. It's just not in the same place as before. So we'll get to some measurements in a second, but that's bigger than 14 centimeters now. It's focusing in a different place. Now, what we need to do is analyze where it's going to be. And we need some data for that. So what we're going to do today is collect some data. And then next lesson, we're going to analyze it and try to work out what's going on. So we're going to take 5 measurements. 5 tends to be about right to see what we need to see. And I'm just going to turn the lights off in the room to make it a little bit easier to see, but I'll still leave a little bit of light coming in so we can see the ruler. Okay, so I'm going to place the object at different distances from the lens, which is going to basically mean that I move the lens rather than the object because it's a lot more movable than the object is. So what I'm going to do is I'm going to start with the lens quite a long way away. So I've got a ruler on the desk in front of me, and I'm just going to take it out to around about 40 centimeters. Well, should we do a bit further? Should we do 45 centimeters? So on your table, you've got a column for the distance between the lens and the object. So on your first row of your table, you can record that the distance between the lens and the object is 45 centimeters. So in that first box, top left, distance between lens and object, you can write 45 centimeters. And you can see on the screen that at 45 centimeters, I don't particularly have a very good image. But if I move this around to the right place, there we go. Okay. So that's pretty much in focus, I think. Yeah. So we just need to measure the distance between that. So the lens is at 45. I don't think you're particularly going to be able to see this maybe through the camera. The lens is here at 45. And then the screen is coming in at 66. Which places the distance between the lens and the image at 66, take away 45. If you just jot down 21 in your next box, which is the distance between the lens and the image. we now need to describe the image. So real means, is there an image? And there is, it's really there. So you can write the word real in the next box. Well, it's not upright, is it? That's not what an F looks like. So it is inverted. So you can write inverted in your next box. And then I think you can see that that F is way smaller than that F. But we're going to be a little bit more scientific about it than that. So you can write the word diminished if you want, but we're actually going to measure the height of the image just to make sure that we've got some data to go with it. So if I just bring the ruler in. And you can see that the height is what? 4.6 centimeters? 4.5? 4.6. And so you can get out your calculator now and you can work out the scale factor, which we call the magnification. So how much bigger did it get? Well, it didn't get bigger, it got smaller. So you're going to end up with a number less than 1 for your magnification. So what we do is we divide the height of the image by the height, the height of the object. Yeah, the height of the image by the height of the object. And that gives us the scale factor by which it's changed by. So you just need to tap into your calculator, 4.5, or maybe you can do this in your head. 4.5 divided by 10. So we get a magnification of 0.45. It's round about half as big as it was. Okay, that was our first investigation. We're going to fill in 4 more rows. Still with me? Want to ask any questions, or shall I carry on? Okay. I'm going to pull the lens back to 28. There we go, lens is sitting at 28. And again, we kind of got an image, but it's a bit fuzzy. It's not in focus yet. So I just need to move this until it is. So there you go. We can get that in focus again. So it's really there. So again, you can fill in that it's a real image, this next one. The object distance was 28 centimeters. And now you can, oops, there goes the lamp. And if we just look down at the ruler, you can see that the lens is sitting at the 56 mark. So 56 take away 28 is 28. So the object distance is 28, and the image distance is 28. And if I just do the measurement of the height, there's your ruler, and you can see that the height of the image is 10 centimeters. So if you record 10 centimeters as your image height, and the object is 10 centimeters as well, so this time it's neither magnified or diminished, it's just the same size. And the magnification is therefore 10 divided by 10, which is 1. Okay, let's bring it in a little bit closer. I'm going to stick it at 21. Spatial lens sitting 21 centimeters away from the object. And again, we've got an image. It's not quite in focus. So let me just move that.
So we can't hear you.
How long haven't you been able to hear me for?
Most of that.
Okay. That would have been nice if you told me that earlier. The whole experiment.
No, not the whole. Just that. Just we got to
Oh, was
we
it
did
when
the
I knocked the
28
lamp?
centimeters one.
The 28
Done 2
centimeters.
rows.
Okay, so you watched me do the last one where I placed the lens 21 centimeters away.
Yeah.
And the image was then 45 centimeters away.
Yes.
And the height came in at 19.6, giving a magnification of 1.96.
Yeah.
All right?
Yeah.
Okay. Okay, so thanks for letting me know. Right, we're on to the fourth one now. And I've moved the lens so that it's at the focal length from the object. So I've actually placed it at the 14 centimeter mark. So the light is kind of coming to the lens from a distance that it's supposed to be focusing the light at, if it was parallel light. And then if we just look at the screen over here, you'll notice that there is some light on the screen. You can see that it's making a fuzzy area, but this time, no matter where I place the screen, all I get is fuzziness. And I just can't make it focus. No matter where I put the screen, I just get a fuzzy area. And so we actually discover at this point that we've reached a limit to what the lens is capable of doing. And if you try to create an image of an object that is closer to it than the focal length, then the lens just can't make an image. So you can see that there is the outlines of a really fuzzy F shape there, but I certainly can't bring it into focus. And now that gets even worse when I bring the lens closer than the focal length. If I just bring it in a little bit, it's got even fuzzier now, and I just have no chance whatsoever of imaging that. However, that doesn't mean that there isn't an image. So for the last 2 rows of the table, you can fill in that the object distance was 14 centimeters, and then it's at about 10 at the moment. So 14 and 10. But in the image distance, you're going to have to write NA. And in the upright or inverted, you're going to have to write NA. Oh, no, leave that one a sec. Sorry, I'm skipping ahead of myself. Right, so NA for the image distance, but let's have a little look with the camera. So although the screen can't form a focused image on it, if I just take the screen away and I bring the camera in instead, there we go. Okay, so there's the F lit up behind. And what I'm going to try and do is make the camera look through the lens. So at the moment, all you're seeing is brightness. But if I bring the camera close enough, hopefully, right, there we go. You're looking through the lens. So there's not looking through the lens. We're looking through the lens now. And you can see that there is an F kind of inside that lens. You can see that it is there. And it's upright. So you can write that in your which way up is it? It's upright. Now I can't do any measurements for you to show you whether it's bigger or smaller. But what I can say is that the only reason you can see it is because this camera that I'm holding in my hand has its own optic system. And so's your eye. And if you were in the classroom now and you were looking through the lens rather than the camera looking through the lens, you'd see the same thing. So an image does exist. The lens has focused the light and it is producing an image of the object. But the only way that the light can be collected together in order to see that image is if you collect the image with your own imaging system, like the one in your head or the one in this camera. So it wouldn't be right to say that there wasn't an image at all, but what we do is we refer to it as not a real image, but a virtual image. So for the last two lines on your table, you need to write that the image is virtual. It does exist, but it doesn't exist in the real world on a piece of paper on a screen. It only exists if you have an imaging system like your eye or a camera in order to reveal that image to you. It's a virtual image. And we'll talk more about that next time. I'm just going to point out at the bottom of the sheet that until the 1st of January, the link at the bottom of the sheet was a really good way to consolidate this lesson. So this link here to an applet called Geometric Optics allowed you to perform this experiment virtually, and it allowed you to take more measurements and more data, and there were loads of cool things that you could do with it to really underline what we've been doing today. Unfortunately, it's a Flash applet, and on the 1st of January, Flash kind of stopped working globally. If you happen to have a dedicated Flash player on your home computer, by all means have a go at that applet. I'm hoping that they'll convert it. They've converted most of their other applets. Maybe this one's just down towards the bottom of the list. But if you happen to have a Flash player, have a go with that. What I do want you to do, though, whether you got a Flash player or not, is between now and next lesson, have a little go to see if you can analyze your data that we've got today to try to come up with any rules about how lenses work. So, for instance, a rule might be, if the object is further away than this, then the image will be, and then describe it to me. But when the object is between this distance and this distance, the image is this and this. Or when the object is exactly at this distance, then it's exactly like this. Just try and come up with some rules to explain to me how the converging lens is producing the image and what kind of image is getting produced. What we're going to do next lesson is analyze this data using a diagram approach, and you're going to learn how to draw some diagrams called lens diagrams, which allow you to predict what's going to happen without actually having to do the experiment. So we'll use the data that we've got to verify that these lens diagrams are accurate and that they work. And then once we're happy that they are, you'll then have a tool in your toolbox to mean that you can always predict what a lens will do. And this is the basis of what an optometrist would do when producing lenses for a specific purpose. However, for today, I think that we are done. All I will say is if you struggled at all with a printer today to print today's worksheets, you really, really do need a worksheet for next lesson. So you're going to have to draw your own next time if necessary. And given that it is merely a horizontal line on a piece of paper, you will be fine if you don't have a printer. So don't stress that for next time. You can just get a blank piece of paper and make your own version of the worksheet. It's just got some horizontal lines on it. Okay, if you want to ask me any questions, now's good. But before you disappear, I just need to finish off the register, which I'm just doing now. So don't go anywhere just yet. Okay, I'm done. So if you want to ask any questions, please feel free to do so. Otherwise, we're done. See you next time.